Hi guys, welcome to the summary video for enthalpy change and Hess law. First, what is that enthalpy change? Now, enthalpy change also can be written as a delta H. All right, this indicates or a symbol for enthalpy change. Now, what is that enthalpy change? Enthalpy change is actually the energy changes during a chemical reactions. Okay. Energy changes. Now, what does that mean by energy changes during the chemical reactions? Now, in a simple chemical reaction, for example, I have A plus B equals to C. All right. So I will split them into two. On the left-hand side, it's always reactant. On the right-hand side, it's always product. Now, what happened when reactants mix together? So when reactants are mixed together, the first thing that happens in a chemical reaction is bond breaking. Okay, bond breaking. And in the product side is actually bond forming. Now, what happens when you need to break a bond? Usually when you need to break something, we will actually absorb heat from the surrounding, right? We need energy to break a covalent bond in this case. So what happens is bond breaking is always absorbing heat, energy, all right? Bond forming is the opposite because you form bond between atoms or molecules. When you form bond between atoms and molecules, usually the stability will increase. Okay, so when the stability increases, you don't need that much of energy in the system, so it will release out energy to the surrounding. So bond forming is always releasing heat. Okay, so bond breaking is absorbing heat, bond forming is releasing heat. Say, for example, absorbing heat. Let's say in this reaction for A and B to react, I absorb 100 kilojoules of energy. All right. And in the bond forming, when you form the product, it releases 50 kilojoules of heat energy. So absorbing heat, I put a plus sign because you absorb into the system, you add in energy. And releasing heat to the surrounding, I put a negative sign because you release the heat to the surrounding out from the system. Okay, so what is the total energy change in these reactions? I absorb 100 and release 50. So the total enthalpy change for this reaction, like I said, delta H, is actually positive 50. Okay, per mole. Because everything in the enthalpy change is always per mole of A or B and per mole of C produced. Okay, I will explain further on that. Why is it always per mole? Now, in this case, the energy difference between bond breaking and bond forming is positive 50. Because I absorb 100, I release out 50. I still have 50 with me. Okay, so this is the energy change. Now, this is not always the case. Sometimes the bond forming here will release more energy than what is absorbed. So if that's the case, the enthalpy change will be negative. All right, so I just give an example for this. For example, let's say you have B plus D equals to E. All right, so bond breaking. So bond breaking, let's say you absorb like positive 150 kilojoules. All right, and on the product side, because bond forming, so you release, let's say, for example, about, this is bond forming. Okay, so it releases 200 kilojoules. All right, so what happened? Absorb 150, but I release out 200. So the difference between bond breaking and bond forming is minus 50 kilojoules per mole. Okay, so this is the enthalpy change of this particular reactions. It's a negative because overall they release heat more than absorb heat. All right, so the next thing is, since we have different sign, okay, enthalpy change. So enthalpy change giving you a positive sign means we call it as an endothermic reactions. Because overall, you absorb heat into the system more than the system releases heat to the surrounding. So if enthalpy change is giving you a negative values, we call that as exothermic reactions. Okay, so exo means exit, you release out energy, endo means you take in energy. So this is how we differentiate between positive enthalpy and negative enthalpies. All right. Now, next things we need to learn about the graph. How does an energy profile diagram looks like when it is an endothermic or exothermic reactions? So we have two graphs here. Let's say I have a reactant, changes into go through an activation energy, you change into product. So this is reactant, this is product. I have another graph where I go through activation energy and then changes into the product, reactants and product. All right, so the x-axis is actually energy. Y-axis, x-axis is actually progress of reactions. Sorry for that. Y-axis is energy. Same goes to this. Energy for y-axis. X-axis is progress of reactions. Okay. Now, what is the difference between these two? Apparently you can see that the energy value of the product here is more than the energy value of the reactants. What does it mean? When the energy of the product is more than the reactant means they absorb heat more than release heat. So this graph is like representing endothermic reactions. Okay, and here the product energy value is lower than the energy value of the reactants. All right, so which means it release heat more than absorb heat in these chemical reactions. We call this as exothermic reactions. Okay, so you must able to differentiate between endo and exo based on the reaction profile diagram. So in this case, how to label enthalpy change? Like I said, enthalpy change is between the energy change between reactants and product. So this is the energy change. We call it as enthalpy, which is a positive value. And here, going down, because from reactants, higher value to lower value. And this is also enthalpy change, giving you a negative values. So this is the energy or reaction profile diagrams between exo and endo. All right, so hopefully it's clear. Let's move on to the next part where we look at standard enthalpy change. Okay, how this looks like, same thing, delta H, but with a knot here. This indicates standard. Now, what is the standard enthalpy change? What is the difference between standard enthalpy change and enthalpy change? Basically, they are the same thing. It's about the energy change in a chemical reaction, just that with the word standard, the reaction actually happen at standard conditions. Now, what is that standard conditions? It's always 1 atmospheric pressure and 25 degrees C. Okay, so these are the standard conditions. And if it involves concentration, then it will be 1 mole per dm cube. That's the standard concentration. All right. And the substances under standard condition, it's always under its most stable physical state. Now, what does that mean by most stable physical state? Example, what is the most stable physical state for sodium? Solid, right? It happened as a solid. It appeared as a solid under room condition, which is 25 degrees C, 1 atm. So what is the most stable physical state for nitrogen? Yes, gas, right? What is the most stable physical state for bromine? Under room conditions, bromine is actually liquid. So under standard conditions, substances or any chemical compounds will always at its most stable physical state. Okay, so this is what we call a stable physical form or stable physical state under standard condition. Okay, so no confuse here. Enthalpy change is exactly the same as standard enthalpy change. It's just that they measure the energy change under standard conditions. All right, so next things we look at thermochemical reactions. Now, what is that thermochemical reactions? Or thermochemical equations, we call that. It's basically a balanced chemical equations. For example, zinc plus HCl, you get zinc chloride plus hydrogen gas, right? Solid, liquid, aqueous, and aqueous, this is a gas. This is under standard conditions, okay? Now, let's say, for example, these reactions, the enthalpy change, the standard enthalpy change is equivalent to positive 100 kilojoules per mole. Okay, it's an endothermic reaction, for example. Now, what will happen if I change the equation like that? Now, what do you see the changes? I multiply the whole equations by 2, right? So what will be the enthalpy change now? The enthalpy change will be multiplied by 2. 200 kilojoules per mole from 100 just now. Okay, now what if I reverse the reactions? For example, hydrogen gas plus zinc chloride changes back into zinc plus HCl. So what will be the enthalpy change here? This third equation is the reverse of the first equation. Reverse means from positive, it will turn into negative 100 kilojoules per mole. From endothermic, it turns into exothermic. So when you reverse the thermochemical reactions, the sign will change. When you multiply the thermochemical reactions or equations with different coefficients, the enthalpy change will change. Okay, so we call these as thermochemical equations, so that we are aware when there's a change in the coefficients, the value of the enthalpy change will change. So this is thermochemical equations. All right, let's move on to the next things. Now, the next part will be all about definitions of different enthalpy changes. Now, why is it definition is important? Now, I will not ask you to define what is enthalpy change of formations, what is enthalpy change of combustions, but it is important to know the definition so that you can construct a thermochemical equations based on the definition. For example, what is enthalpy change of formations? All right, so enthalpy change of formation means delta H, put a small little f here, a subscript, indicates formations. So what is the definition for it? 1 mole of substance or compound formed from its element under standard conditions. Now, this is definitions for this. Sorry, I forgot to put the not and the word standard. All right. Now, this is the definitions. Now, what is the keywords here? 1 mole of substance formed from its element. So let's try. If I ask you to construct an equation for, let's say, what is the enthalpy change of formation for carbon dioxide gas? Formations of carbon dioxide gas. According to the definitions, 1 mole of carbon dioxide gas formed from its element. Element means the standard state. So what are the elements involved here? Carbon and oxygen. So carbon plus oxygen gas. All right, and then we balance the equation. Just nice. 1, 1, 1. So this is enthalpy change of formations of carbon dioxide gas. Okay, 1 mole of substance formed from its elements. Let's go give you another example. What will be the formation equations for water? Then we put it in. 1 mole of substance, in this case is water. So 1 mole of water formed from its element. I have hydrogen here, it's hydrogen gas under standard conditions, plus I have O here, so definitely O2. All right, obviously it's not balanced, we have to balance it. Now, how to balance it? We put half. Okay, so this is enthalpy change for formations of water. Now you may ask, instead of putting fractions of half oxygen, can I just multiply by 2? For example, I have multiplied by 2, this one will become 1, and then 2 water. The answer is no, because if that's the case, after you multiply by 2, how many mole of substance actually form here? 2, which is against the definitions of 1 mole of substance form. So you must able to maintain the 1 mole of substance formed from its elements based on the definitions. Then only you get the right equations. So always remember the product side is always 1 mole. okay, then only you balance the equations. You can't actually change it into 2 moles, 2.5, 3, or 4. That is wrong. All right, so this is enthalpy change of formations. Now, what about enthalpy change of combustions? So I just put a short form, enthalpy change of C, combustions, standard conditions. Now, what is the definition for this? 1 mole of substance, okay, 1 mole of substance burned in excess of oxygen under standard conditions. Okay, again, the keywords is 1 mole of substance burned in excess of oxygen. So what will be the equation like? For example, what is the combustion equation for hydrogen gas? All right, so hydrogen gas, 1 mole of hydrogen gas burned in excess of oxygen, you're forming H2O. And then you balance the equation. Again, guys, they said 1 mole of substance burned in excess of oxygen, which means the one that burned with oxygen must maintain as 1 mole. If that's the case, you have to put a half here instead of multiply the whole thing by 2. So this is actually the combustions of hydrogen gas. What about the combustions of sulfur? Okay, so what would be the equation for combustions of sulfur? Again, 1 mole of sulfur plus excess of oxygen, you get sulfur dioxide gas. And then balance the equation. Yes, just nice, it's balanced, and make sure this is maintained as 1 mole. 1 mole of substance burned in excess of oxygen. Now, anything given, guys, anything given, when they say combustion means you maintain that substance as 1 mole, plus with oxygen, should be in excess, and then you get whatever product it is. Okay, so this is enthalpy change of combustion based on the definitions. And let's move on to next, which is enthalpy change of hydrations. Now, what is the definition for hydrations? 1 mole of gaseous ions dissolved in large amount of solvent, or in this case, usually water, under standard conditions. Again, I forgot to put a not here. That indicates standard conditions. So, based on this definition, can you construct out equations for hydrations? 1 mole of gaseous ion, anything, right? 1 mole of gaseous ions dissolve in large amount of solvent or water. So, for example, 1 mole of gaseous sodium ions, for example. So, 1 sodium ion in a gaseous state, 1 mole of gaseous ions dissolve in large amount of water. I don't put in the H2O because they are just plainly dissolved. If you put the H2O in, okay, it doesn't matter because at the end you will still get water. The sodium is dissolving it, but not reacting with it. So I skip the water. So Na plus gas, I dissolve in water. I put it on top of the arrow so that I don't have to balance it. What would you get in terms of the physical state? Gaseous ion dissolve in water. You will change into sodium ions, aqueous. See the physical state change from gaseous into aqueous because it dissolves in water. Is there reactions between sodium and water? No, because water is still water. At the end, sodium ion is still free-moving sodium ions in the solutions. So therefore, I don't put the water into the equations and trying to balance it. No. All right, so let's say for another one. 1 mole of gaseous ion dissolved. What is the hydrations of fluoride? So fluoride is F minus gaseous, 1 mole, because 1 mole here. And then dissolve in water, and what do you get? Still the same, 1 mole of fluorides, but from gaseous it turns into aqueous. That's it. This is enthalpy change of hydrations. All right, so let's move on to another one, which is enthalpy change of standard solution. What is enthalpy change of solution here? More or less the same as hydration. But in this case, they put 1 mole of substance instead of gaseous ions. Dissolved in large amount of water. Basically, they are the same. just that one is ions, one is substance. Of solvent or water under standard conditions. Okay, example, any substance, guys. So for example, 1 mole of sodium chloride. Obviously, it's a solid under standard conditions, room temperature, salt, right? So, and then what happened when they dissolve in large amount of water? Sodium chloride is a soluble salt. So again, I don't put water in it because they're not reacting, they're just dissolving. So you will get what? Sodium chloride aqueous. See that? You can write in this form, or you can write sodium ions aqueous in a separate form, Cl minus aqueous. Either one acceptable. Okay, so this is the enthalpy change of solutions for sodium chloride. Okay, now what is the enthalpy change of solution for magnesium chloride or magnesium oxide? So the equation will be MgCl, MgO, because magnesium oxide, solid, of course, standard conditions. And what do you think? Plus liquid, and then you get magnesium oxide aqueous. Or magnesium 2 plus aqueous oxide aqueous. But actually, this is not a good example because magnesium oxide, when they react to the solubility of magnesium oxide in water is actually quite low. All right. So as long as they are changing from a substance, okay, into aqueous form, they dissolve in water or any solvent, that what we call a enthalpy change of solutions. Okay, so this is definition for solutions. Let's move on to enthalpy change of standard atomizations. Now, what is that atomization? Basically, you're converting any compounds or any substances into gaseous atom. It can be a molecule, it can be ions, doesn't matter. At the end, it will change into gaseous. For example, let's give the definitions. Okay, for atomizations, when an element or compound converted into 1 mole of gaseous atoms under standard conditions. This is atomizations. Can you name that? Any elements or any compounds. For example, I have bromine. Okay, bromine is a molecule and is a liquid. All right, under standard condition. Please make sure you put in the proper physical states. And then what do you get? You will change it into 1 mole of gaseous atoms. See the difference? Br2 converted into Br. One is a molecule, on the left-hand side is a molecule, and on the right-hand side is an atom, single atom. But this equation is not balanced. So how to balance it? Then some of you may ask, okay, just put 2 here, right? 2Br. Is that the right equations? If you put 2 here, that means 2 mole of gaseous atom form, which is against the 1 mole from the definitions. So this is not the right equations. The right equation should be Br2 liquid, the element under elemental state standard conditions, half you turn into 1 mole of gaseous atom. Then only you can get 1 mole of gaseous atom. Okay, so this is the right equations for atomizations. All right, let's move on to another one. We call that as, this one is quite familiar, enthalpy change standard conditions of neutralizations. So what is that? Neutralizations is actually the energy change when 1 mole of water form from a reactions between an acid and base. Or sometimes we call base as alkali. Alkaline is actually a base that is soluble in water. Example, NaOH, KOH, right? Acid, HCl, H2SO4, HNO3. As long as an acid and a base react together, you get 1 mole of water, and that energy change, we call that as enthalpy change of neutralizations. All right, so this is the definitions. Now, what will be the equations looks like? So for example, between acid and base, so the simple one is HCl plus NaOH between an acid and base, and then what do you get? You get NaCl plus H2O. Is the H2O 1 mole? Balance equation? Yes, it's 1 mole. So no matter how, you have to make sure that the mole of water is 1 mole. Then only is the right equation for enthalpy change of neutralizations. Okay, so next, move on to the next definitions. We have another 3, which is less important, but let's go through it quick. First is enthalpy change of lattice formations. Okay, and then the second one is enthalpy change of ionizations. We learned that in topic number 1. Next is enthalpy change of electron affinity. Okay, now what is that lattice formations? All under standard condition, guys. All right, so let's just give you an equations. Lattice formation means basically you're forming 1 mole of ionic compound. For example, NaCl, solid. You're forming 1 mole of NaCl from what? From the gaseous ions. Na plus in a gaseous state plus Cl minus in a gaseous state. So this is lattice formations. Maybe I'll give you another example. Let's say I want to form lattice formations of magnesium oxide. Again, it's a solid, right? So what will be the things here? 1 mole of ionic compound formed from its gaseous ions. So what are the gaseous ion here? Mg. So Mg2 plus gas plus oxygen, O2 minus gas. So make sure it is gaseous ions. Combine them, you get 1 mole of ionic solid. So this is lattice formations. And ionizations, I believe everybody knows about this. What is ionization again? For example, ionizations of sodium. So 1 mole of gaseous atom change into 1 mole of gaseous ion with the removal of electrons. That is ionizations of sodium. What about ionization energy of chlorine? Again, 1 mole of gaseous chlorine atom. Remember, it's an atom, gaseous atom. Convert into Cl positive gaseous ions because you are removing electrons. Ionization is always remove electrons plus 1 electrons. So this is ionization energy or enthalpy change of ionization for chlorine. Okay, what about electron affinity? Electron affinity is the opposite of ionization, which means you're adding electrons into a gaseous atom. So let's say, for example, I have gaseous atoms of oxygen. Okay, I'm adding electron in means I add electrons, and then what do you get? You get O minus gaseous ion. This is the first electron affinity of oxygen. Okay, and then you can further add on another electron because oxygen needs 2 electrons to achieve stable configurations. So from O minus gas plus E again, second electrons added in, you get O2 minus gas. This is a second electron affinity. All right, so electron affinity is the energy changes when you add electrons into an atoms or an ions. Ionization is remove electrons from atoms or ions in a gaseous state. Lattice formation is formations of ionic compound from its gaseous ions. All right, so these are the 3, which is the last definition we need to know for constructing thermochemical equations. All right, so let's move on to the next. Now, this is the important part. Once we learn all the definitions, we know how to come up with equations, we learn about calculations. Now, calculations divided into 3 parts. Number 1. Calculation means to calculate enthalpy change. All right, enthalpy change of reactions. Any reactions, which means can be combustion, formation, neutralization, lattice formation, whatever definition that we learn. So in general, they put enthalpy change of reactions. How to do that? And the unit for it must be kilojoules per mole. All right, so the first method is to use MC delta T. Okay, obviously this is a data. You must get the data from the experiments. So MC delta T, you get the heat change divided by the mole of limiting reagent. I'm sure by now you should know what is limiting reagent. So when you calculate MC delta T, you will get joules, all right? And then divided by the mole of limiting reagent means per mole here, all right? So you will get your answer in joule per mole. And then divide by 1000, you will get your answer in kilojoules per mole. So it must be in this unit of kilojoules per mole. This is the first method. I guess I don't have to further explain on what is MC delta T because I explained that during our lab session for this week. All right, this is the first method to calculate enthalpy change. Now, what is the second one? Okay, calculations for enthalpy change of reactions. Again, you guys may ask, because I keep writing standard, right? Now, what if they remove the not? What if they just say calculate the enthalpy change of reaction without the standard? It is the same thing, just that they're telling you without the standard conditions. This reaction conducted under a non-standard conditions, but the calculation-wise is the same. All right. So the second method is to use Hess's law. Now, let me briefly explain what is Hess's law. Hess's law is something like that. Let's say, for example, from A, I need to change it into C. The energy involved here is 100 kilojoules per mole. That's the enthalpy change, right? And what if I don't want to change directly from A to C? Let's say A change to B, then B change to C. You have two energy here, A and B. Kilojoules per mole, kilojoules per mole. Okay, guys, under Hess law, it defines that, it actually states that the total energy in a chemical reactions or the total energy change in the chemical reactions is the same regardless of its pathway, which means as long as it's a reaction changing from A to C, regardless of whether A changed to B, B changed to E, F, G, H, I, J, K, then come back to C, as long as it's A to C, all right? Regardless of how many intermediate in between, the total energy involved is always 100 kilojoules per mole. Therefore, we can conclude that based on Hess law, A plus B from the energy given here, from A to B, you get energy of A, from B to C, you get energy of B, right? A plus B is always equals to 100 kilojoules per mole. See that? So regardless of its pathway. Now, this is the concept. Okay, this is the concept. So we make use of Hess law to calculate an enthalpy change without carrying out an experiment. Because the first method just now was MC delta T. You need to have an experiment data before you can calculate. But using Hess law, you don't need experiment. We can calculate based on the standard value. Now, how does it look like? I show you now. Examples, all right? Let's say C3H8 plus O2. Okay, you get carbon dioxide and water. Combustions of propane. So balance equation, 3 carbon dioxide gas, 4 water, and then oxygen will be 5. So this is how you balance it. Usual way. What is the enthalpy change of combustions of these reactions, of these particular equations? Calculate the enthalpy change of combustion for these reactions of propane. Given, in the question, they must give you information. Given what? Enthalpy change of formations for propane is, let's say, 1222 kilojoules per mole. Okay, negative. And then enthalpy change of formations for carbon dioxide gas, which is -386 kilojoules per mole. No worries, all these values are given in the questions. Next is enthalpy change formations of water is -286 kilojoules per mole, for example. Okay, I just made up the values, guys. It's not the exact one. So this is how the question looks like. How to calculate the enthalpy change of combustion here, given that the formation of propane is this, formations of carbon dioxide is this, formations of water is this. All right, let's check it out. Remember all this, right? So we're going to start up with the calculations. I have to erase that because I need space. All right, so yeah, come back to the same thing. So first information they give is formations of C3H8, right? Second is formations of carbon dioxide gas. Third is formations of water. So what is the first thing you need to do? You need to construct the equation for each of this. What is the equation for formations of C3H8? Now you need the definitions. 1 mole of compound formed from its element. So C3H8, 1 mole. From its element, what are the elements involved? Carbon plus hydrogen gas. Not H, but H2 under standard condition. What is the most stable physical state of hydrogen? H2 gas. Make sense? So is it balanced here? Obviously not. I need 3 carbons and 4 hydrogens. Make sure the product is 1 mole according to the definitions. What about carbon dioxide? Same thing. 1 mole of carbon dioxide gas formed from its element, carbon plus O2 gas. Is it balanced? Yes. Formations of water. 1 mole of H2O formed from its element, hydrogen gas plus O2 gas. Is it balanced? No. Balance it half. Make sure it's 1 mole. Done with 3 equations, right? Okay. Next, draw a line. And what was the equation they want you to calculate again? C3H8 plus O2, the one that I written out just now. You get carbon dioxide gas and water, because this is the reaction they want you to calculate. So 3, 4, and 5. All right. So to apply Hess law, this is the simple way. So we write out the 3 equations given and total up, you should get the final equations. Follow how should I do that step by step. Number 1, we check this, the final equations that we want. So C3H8 1 mole. Where do we get C3H8 1 mole from these 3 equations? There you go. Let me change the color. You have this, right? Okay. Now this is a reactant. The one here is the product. So they have opposite directions. So what happened if you have opposite directions and both 1 mole? The value given for this just now was -1222, right? Kilojoules per mole. So since they have opposite direction here, I change this into a positive. Circle this value. All right. Next, oxygen is in standard condition. Ignore. We don't have to care about this. Next, carbon dioxide gas. Where do I get carbon dioxide gas? Here. I need 3 moles of carbon dioxide gas here. How many mole here? 1. So this need to times 3. So the value given is -386. You need to times 3. Make sense? I have 3 here. I only have 1 here. So the value is for 1. I need to times 3. And do I need to change the sign here? This is a product. This carbon dioxide is also a product. So both products, same direction, same side, we maintain as negative. Circle this. All right. And water. We need 4 moles of water. We have water here, but just 1 mole. So the value given, -286, you need to times 4 because I need 4 moles. And this is a product. This is also a product. So maintain the sign as negative. Don't change it. Now you have 3 circuit value here. So what is the enthalpy change of combustions for this particular reaction? You just add them up. All the circuit value, you just add them up, which means equals to positive 1222 plus with -386 times 3 plus with -286 times 4. then you total up, you get your final answer as kilojoules per mole, and that's your answer. So this is how you calculate enthalpy change based on the information given. All right, so let's give you another example. Maybe this is a bit confusing for the first time. Let's say we have carbon plus hydrogen. This is given solid. Change into C2H6. Let's say, for example, gas. So what is the enthalpy change of formation for these equations? Is it balanced? No, sorry. 2, 3, right? So what is the enthalpy change of formation for these equations? Unknown, right? But they give you informations. What information given? For example, enthalpy change of combustions for carbon, enthalpy change for formations of combustions of hydrogen, and enthalpy change of combustions of C2H6, for example. And the value given is carbon -392, for example. Combustions of hydrogen is -286, and then here is given as -222. 2222, right? So these all in kilojoules per mole, guys. All in kilojoule per mole. And these are the information given, and this is what they want you to calculate. What is the enthalpy change formations of this? Follow the method just now. First, write out the equation for these three. What is combustions of carbon? Back to the definition. Combustion means 1 mole of carbon, excess of oxygen, you get carbon dioxide gas. The value is -392, balance. What is the combustion of hydrogen? 1 mole of hydrogen burned in excess of oxygen, you get H2O, balance equations, value is -286. What is the combustions of C2H6? 1 mole of C2H6 plus excess of oxygen, you get carbon dioxide and water, right? This is a product and balance equation, 2 carbon dioxide, 3 water, and you have 4 plus 3, 7, 7/2 oxygens. And the value is -2222. Okay, so let me rewrite that so that you won't confuse the 2222. I put it on top later. So this is -2222. All right, all values given and all equation done. And what to do next? Draw a line and rewrite this equation that we are calculating here. 2 carbon plus 3 hydrogen, you get C2H6. And what is the value here? Start comparing like just now. Okay. First, we start with carbon here. I have 2 carbon. Where do I get carbon? Here. Reactant, same side. All right, same side. Maintain negative, but I have 2 mole here. So these value times 2, circle. Next, hydrogen. Where is hydrogen? Here. I have 3 hydrogen. Here only have 1. Both on the same side. Reactant. Don't change the sign, but just times 3. All right. And last one, we have C2H6. Where do I get C2H6? Here. Both 1 mole, but one is a product, one is a reactant. So we have to change the sign from negative to positive. Circle this value. And what is the final answer here, guys? Add up all 3 values here. So basically, the enthalpy change of formation for this is -392 times 2 plus with -286 times 3 plus with 2222. And then you will get your enthalpy change of formations. So this is actually how we calculate Hess law, how we calculate enthalpy change using Hess law. All right, hope it helps on this. In tutorial, I will explain more in that case. All right, this is the example given. So this is the second method of calculating enthalpy change, and we have the last one. for enthalpy change of reactions, any reactions. So what is the third method here? The third one is using bond enthalpies. Now, what is that bond enthalpy? It's also known as bond energy. Right? Now, this one you have to refer to data booklet. And what is the bond energy for them? So let's start with a simple example. Okay, let's say I have CH4 plus O2. I'm getting CO2, plus H2O, enthalpy change of combustions, right? It's combustion here. And then we balance the equations, 1 carbon, 2 water, and 2 oxygen. Done. Now, what is the enthalpy change of these reactions? How to calculate? Nothing is given, guys. In this case, nothing is given. Not even enthalpy formation for anything. Like just now, I give you a lot of information, right? In this case, nothing is given. They just ask you to refer to bond enthalpies, which is this, in your data booklet. So in this case, we're going to do this. Split that into two. Still remember, left-hand side, reactant is always bond breaking. On the right-hand side, the product is always bond forming, right? So let's calculate total energy for breaking and the total energy for forming. Let's start with the left-hand side, bond breaking. So how many bonds we need to break? CH4 is actually CH4, like that, right? Water is actually, oxygen is actually O double bond O. See that? So this is a structure. Then only we know what are the bonds that we need to break. So how many CH bond here? 1, 2, 3, 4. So we need to break 4 CH bond. What is the value for CH bond energy? Check data booklet. It's actually 413. This is the energy given in data booklet for CH bond. All right. Plus with oxygen, O double bond O. What is the energy for O double bond O? In your data booklet, let me check the data booklet. I don't have the data booklet here. Okay, just a minute. If not mistaken, it's 496. Just put in the value. Oxygen 496. How many oxygen do we have here? 2 moles, right? 2 times 496. You got that? The coefficient is important to times in because 2 molecules. This energy 496 is for breaking 1 molecule of oxygen, a double bond. If you have 2, then of course you have to times 2. And add them up, you get the total energy here. So what is the total energy here? Let me calculate it. 4 times 4, 13. You get 1652 plus 496 times 2, you get 992. So 992 plus 1652, you get 2644. Okay, now this is a bond breaking, am I right? So it's always positive. So I have positive 2644 on the left hand side. And do the same thing on the right. Carbon dioxide is C double bond O double bond O. H2O is OH2, like that. This is water molecule. And then I have 2 molecules of water, of course. Now, what to do? Add the total energy up. So for C double bond O is 743. I have 2 here. So 2 times 743 for C double bond O, bond energy. Plus with how many OH bond here? 2. 2, and then you have 2 more of water, means 2 times 2, 4. So 4 OH bond, which is what is the OH bond here? Again, you will need to actually check the data booklet. All right, so let's make it a made up value. For example, the OH bond energy is 789, right? Example, all right? So you times it in, all right? So 2 times 743, you get 1486 plus 4 times 789, you get 3154. 3156. See that? And what do you get? At the end, 3156 plus 1486, you get total of 4642. And this is bond forming, so it's negative. So I get 4642 negative here. So done on both sides, we have to calculate the overall energy change, which is the enthalpy change of these reactions. Okay, the methane plus oxygen. So what is that? You always use this. Left values add up with the right value, negative 4642. Just put it in with the sign, positive, negative. You add them up. When you add them up, you automatically getting the answer, which is 2644 plus minus, you get minus 4642. You get a negative 1998 kilojoules per mole. So this is the overall enthalpy change of these reactions, which is an exothermic reactions. See that? So this is how you use a bond energy to calculate an enthalpy change for a given reactions. Now, this is just a simple equations here. This one. All right. They can give you any equation as long as you calculate every single bond energy on the left, every single bond energy on the right, put that positive signs on the left, negative signs on the right, and then you add them up. Like what I did just now, you will get the enthalpy change. So this is the third, which is the last method to calculate enthalpy change. All right, I guess that's it for the summary. I've talked a lot. What is the time? It's about 15 minutes, guys. So this is a summary for enthalpy changes, mainly based on definition as well as calculations. I will discuss more in the tutorial sessions, right? So thank you for watching.